All right, welcome back to the channel. If you're new here, I haven't posted since last December when I had my 112 term project, and I probably won't post after this, but like, comment, subscribe, all that jazz. So today we're going to talk about computational social choice. This is a very interesting field that looks to bring together computational complexity and social choice theory. So today we're specifically going to talk about voting schemes, and we're going to show that dictatorships are the only fair voting schemes. Very exciting. So before we get into that, we got to set up the things that we're going to prove. So first, we're going to have our set of voters is going to be a finite set. We're just going to index using the natural numbers. And then we're going to have, this is referred to as A in the literature, it's going to be the set of candidates. So in our pseudo election, we're going to have Professor Anil Adha as one candidate. We're going to call him A. We're going to have a random Turk as the next candidate. If you know, you know. We'll call him E. And then we have some kind of politician, I think. No stigma there, but we'll call him B. And then we're going to have something called a social choice function. So this is probably the most important part of any voting scheme. This is the function that maps a profile, which is, we'll describe this notation later, to one of the subsets of our candidates, and it's going to be a non-empty subset. So our function is going to take a profile, and what we mean by a profile is a set of all ballots, one for each of our voters. So we're going to have n many voters, and each one of these voters is going to have a ballot. So what we mean by a ballot is, suppose Kanye West is one of our voters. Obviously, Kanye West is going to favor Donald Trump. So he's going to put Trump as his first choice candidate. This is just an informal way of describing a ballot. So he's going to have Trump first. Let's say he likes computational complexity. So he's going to put Professor Adha second, and then he's going to have the Turk last. Yep, sounds good. So obviously, this is going to be known as a ballot. And for every such voter, we're going to have a specific ballot. It's just an informal, strict ranking of the alternatives or the candidates. So we will have a set of all of these ballots. And this is what we pass into our function. This is what our function takes in as input. So it's going to take in all these ballots, and then it's going to output one ranking. This is going to be the aggregate ranking of all the ballots. And whichever alternative or candidate is first in that ranking will be the quote unquote winner of our election. Now, we have a couple of adjectives we're going to use, or a couple of properties, sometimes known as axioms, that we want our social choice functions to satisfy. One of them is, suppose F always chooses the top ranked alternative for all of our voters. Then we call F unanimous. So this is pretty simple, pretty self-explanatory. Now, suppose for all voters, again, is a dominant strategy, shout out to game theory, to provide truthful ballots. So what we mean by truthful ballots is, let's say Kanye West. What we're saying is that Kanye West does not have an incentive to, let's say, swap these two voters, to prefer Professor Adha first and Donald Trump second. Even though Kanye knows that he would rather have Trump be the voter, maybe he would want to lie about his preferences because for some reason, the Turk won the election. Some random crazy ballots, a profile was such that the Turk won the election. Well, this guy is obviously the least preferred alternative for Kanye West. But suppose Kanye switches Professor Adha and Trump, and then the outcome of the election changes to Professor Adha winning instead of the Turk winning. Well, now Kanye West has an incentive to change his ballot, because even though he favors Trump first, Adha second, and the Turk last, he doesn't want the Turk to win. So he might just lie and put Adha first, and then Adha wins. So this is what's known as a manipulation, and this is what we want to prevent. So in this case, going back to the formal definition, this means that if for all the voters, it's a dominant strategy to not lie, i.e. to provide a truthful ballot, then we say that F is strategy proof. This is kind of a strange word, but it is a very common word in voting schemes and computational social choice, also game theory. Next, we have consider one voter, just a singular voter. We'll call him R. We refer to Kanye West as R. It's kind of foreshadowing something in the future. But we will say that if for all profiles P, so for all possible sets of all the ballots that we could possibly send into our social choice function F, we will say if the output of F, which is an alternative, so this is just we're kind of abusing notation in this sense and saying that whatever set that our social choice function returns, we'll just pick the first element in that set, call it A, and that'll be the winner of our election. So if for all profiles, the winner of the election is A, such that A is the top ranked candidate in voter A's ballot, then F is a dictatorial voting rule. So this is pretty easy to see because it's saying that no matter what the preferences of all the other voters are, we always output the top ranked candidate of only voter A's ballot. So voter A only really matters. And we can see kind of easy, I guess, transitivity in this point. We call A dictator. So in this case, suppose we go back to the Kanye example. And then if we say that Kanye West is a dictator, then we're saying that for all possible profiles, for all sets of ballots, the output of the election, the winner of the election is this guy. We'll leave it up to the readers for how they interpret that. But that would mean that Trump would always win every single election if we say that Kanye is a dictator. For all social choice functions, for all choices of any function that maps profiles to winners of elections, Trump would be the winner. So an interesting theorem, the one that we're going to prove in this lecture, is the Gibbard-Satterthwaite Theorem. Quite a mouthful, but what essentially they state is that suppose there are at least 3 candidates. So in our case, we had Professor Haddad, the Turk, and Donald Trump. And we allow any strict ranking of these candidates. So this is essentially to make sure we don't have some like egregious ties. The Gibbard-Satterthwaite Theorem says that the only social choice function that is unanimous, so always outputting the top ranked candidate, and strategy proof, i.e. not manipulable, is, you guessed it, a dictatorship. And this is kind of groundbreaking. So this is telling us that, well, clearly we would want our voting rules to be not manipulable, right? We want every single voter to cast their honest to God, their true, sincere ballots. But what this theorem is saying essentially is that the only way to ensure that is either to have less than 2 candidates or have a social choice function that isn't unanimous, that doesn't output the top ranked candidate. In which case it's like, well, why would we output the second ranked candidate if the top guy's there? Wouldn't we want him or her to be the winner of our election? So this is kind of a like paradigm shifting theorem. It's kind of built off of Arrow's impossibility theorems in social choice theory, which kind of founded the modern social theory aspect, but that's beyond the scope of this lecture. So what we're going to do is try to prove this theorem. And in order to do so, there's going to be a lot of moving pieces. And so we'll try to present a high-level overview of the proof of what it should look like before delving pretty deeply into the intricacies. So first, we are going to say, let's consider an arbitrary profile with Donald Trump. We'll call him candidate B in the future, but just recall it's Trump. Ranked last for some unknown, some crazy reason. He is ranked last on everyone's profile, okay? Let's imagine that voters sequentially, so one by one, boost Trump to the top of their ballot. So what this is saying is that first, with voter 1, we're going to do this kind of pairwise swap where we keep swapping Trump until he gets to the first rank in the ballot. So this maintains the relative order of all the other candidates, but it just puts Trump at the beginning. All right, and then we're going to denote by R, who is a voter. The first voter whose boost causes Trump to win. So obviously in the beginning, Trump is last on everyone's ballot, right? So no matter what, like no matter how bad your social choice function is, you're never going to choose Trump because we're guaranteed that that the social choice function is unanimous, right? Because we're trying to prove Gibbard-Satterthwaite, and they say, suppose we have a unanimous SCF. So we're definitely not going to choose Trump in this way. But once we boost Trump to the top of each ballot, one voter by one voter, eventually there's going to be a singular voter whose boost causes Trump to now be the winner of the election. And we're going to refer to that voter as R. In this case, we kind of made Kanye R, and so this is just, I guess, for comedic purposes, but just kind of envision that R is going to eventually be the dictator that we use to prove the theorem. So kind of it makes sense to show that, all right, if Kanye really likes Trump and Kanye's a dictator, then Trump will always win. So it's just kind of to keep the idea in the back of your heads. So we're going to, once we dive into the actual proof, first we're going to show that if the first R many voters rank Trump first, then Trump is going to win. Kind of conversely, if the last R many voters rank, sorry, not the last R, because we don't know that R is exactly half, but if essentially voters R to the end of the voters rank Trump last, then Trump does not win no matter what. And then we're going to pretty much show that R is a dictator. And in this case, we're going to break down into the special case where everyone puts Trump last. So this is like before the boost. We're just going to arbitrarily consider that everyone puts Trump last and still show that R is a dictator or that R gets his top choice. And then we're going to show more generally, if R chooses either Trump or some random other alternative, some other candidate. By the way, we can use the terms alternative and candidate interchangeably. It's always used in the literature. So we're going to show that if R chooses B or K, this implies that B or K is the winner of the election, thus pretty much defining that R is a dictator because he always gets his first choice. And then we're going to show that Trump wasn't unique. He wasn't special. Who knew? We're just going to show that this could have been the case for any of R's choices. And this is going to complete the proof that the Gibbard-Satterthwaite theorem holds. And I think that'll be a pretty interesting result because one thing to note is that this theorem is, the way that we're going to prove this theorem is actually independent of any social choice function. So even though it says like the only SCF is that satisfies this is unanimous and that is unanimous in strategy proof is a dictatorship, the way we prove this theorem is going to consider an arbitrary SCF. So there's a lot of talk in the literature about like different kinds of voting schemes. If you watch Professor Procaccio's lectures, there's like the board account, there's the majority rule, there's plurality, there's a single transferable vote. So there's tons of different voting schemes, but the way we prove this theorem is going to be kind of voting scheme agnostic, if you will. It'll be independent of any social choice function, and that's a really interesting result because you can just arbitrarily say, let's consider some random social choice function that is unanimous and strategy proof. And then we're going to show that no matter what, you always get the choice of one person. You get a dictatorship. And that's pretty fascinating. It's going to, initially, when I first read the proof, I thought it revealed quite a bit about the inherent flaws of democracy. Which is kind of crazy to think that computational complexity can imply like flaws in a political scheme. But once we show this theorem, we're kind of going to take a step back and find ways to circumvent it because the proof is theoretical because this is 251, obviously, right? So even though the result is, I guess, kind of abysmal, like saying no matter what, you will always get the result of one voter, you'll always get whatever one voter wants, seems kind of counterintuitive to the whole point of democracy. We'll show that this is actually not really tractable in practice, and that's kind of why democracy hasn't been broken yet. But still, the proof is pretty cool. So diving into the proof. First, we're going to take, obviously, an arbitrary, unanimous, and strategy-proof social choice function. So we want to show that one of the voters must be a dictator. And just to reiterate what that means there exists one voter such that the outcome of the social choice function is always the highest ranked candidate from that voter's ballot for any profile. So for any number of people with any number of preferences, that one voter is always going to get his top ranked candidate as the winner of the election. Okay, so first we got to make an observation. So I'm going to call this the big boost hypothesis. It's known as monotonicity in the literature, but that's kind of monotonous, pun intended. So we're going to call this the big boost hypothesis. So suppose there's an alternative that is the winner for an arbitrary profile. We're going to adjust the profile by raising some other candidate, right? Not A, but some other guy. Imagine this is Trump. Imagine Professor Adal won the election. Now we're going to raise Trump, or B, in voter I's ranking. So some random voter I in voter I's ranking for an arbitrary voter I. All right. Remember that everything else is fixed. So all other voters and their ballots are not unchanged. It's only voter I's ranking. We're going to raise B. Okay. So then we claim that either Professor Adal or Trump is the winner of the election now. So just by changing one voter's ranking, we can claim that either that new guy, Trump, or the old winner, Professor Adal, is the winner of the election. All right, now let's prove this observation. So to prove the big boost hypothesis, we're going to say, assume there exists a third candidate that is not Professor Adal or Donald Trump. We'll call this the Turk. We refer to him as E, but you can just think of it as C right now. So C is such that C is the winner of the election after we boost Trump, right? So this is kind of like contradicting this statement. So there are two cases. The first case is that this notation essentially means that candidate A is ranked higher than candidate C. This is actually the notation for a linear ordering. So this is how you formally define preference rankings, or they're also called ballots. Preference rankings and ballots are interchangeable. So saying so this statement is essentially saying that for voter I in voter I's ballot, candidate A is ranked higher than candidate C. Okay, so if it was the case that candidate A was ranked higher than candidate C and candidate C won the election, then I would have modified the new ballot. I would have he would have altered his new ballot so that he could get A to be the winner. On the other case, if voter I actually preferred C to A, then he would have modified his old ballot to get to this new ballot. He would have put C way before A. So why is this an issue? Well, recall our initial hypothesis, our initial assumption. We assumed a strategy-proof social choice function. So this is an issue because it violates the strategy-proof assumption. And essentially, all you need to recall is that strategy-proof is equivalent to manipulability. So I think that's important to write down. So strategy-proof is kind of like manipulability. And what this is saying is that, well, if either of these things were to happen, so after we boosted some guy pretty high up, and then we found out that some third alternative actually won the election, well, then there's only two cases. Either we initially preferred our old person, Professor Adal, not an old person, our initial candidate to the new winner, in which case we would have modified the new ballot to make Adal the winner, or it was the case that we actually liked this new winner instead of Professor Adal. So in that case, we would have modified the old one. In both cases, what we have is that there's an incentive for voter I to manipulate, i.e. to lie about his ballot, which contradicts our assumption. Right? So we have proven the big boost hypothesis. So this is a check mark. We got it. So this is in our belt. We will use this quite extensively throughout the proof. So step one, we are going to consider an arbitrary profile with strict rankings. So you can't say that two candidates are tied in your ranking. You have to always rank one above the other strictly. So we're going to say that there exists Trump, which is in, this is a typo. So this is in the set of alternatives, which is A, such that Trump is ranked last on all the ballots, again, for some unknown reason. Right. So note that this guy is not chosen as a winner. Trump is not the winner initially. Why is this? Well, our other assumption is that our SCF is unanimous. So unanimity means that you always choose the top ranked alternative of everyone. So this contradicts unanimity. Anonymity, actually. I can't speak. All right, so this contradicts unanonymity. Unanonymity. That's a hard word to say. Anyway, starting with voter 1 and all the way to the last voter, we index by the natural numbers, but recall that our set of voters is referred to as n, so it's the size of n, in order, so sequentially. We're going to make Donald Trump the top ranked alternative, the top ranked candidate. Of course, we're going to keep all the other relative rankings the same. So we are going to, like we discussed before, we're going to have R denote the voter such that moving B to the top of R's ballot causes B, or Trump, to now win the election. We're going to refer to R as this, we're going to introduce some new terminology here, the pivotal voter. So in the literature, when they prove the Gibbard-Satterthwaite Theorem, they use this exact term, pivotal voter. And this is kind of, I guess, hinting at the fact that R is going to be our eventual dictator. So let's kind of map out what the profiles look right now, because it's kind of confusing to see a bunch of these things as just, I guess, mathematical formalizations. It's a lot easier to see them in terms of profiles. And what we see is that profiles can easily be displayed in this way. So we have the voter number indexing from 1 to the size. Also note that n equals little n. So just for convenience, we might switch between this notation. And what we're going to have is that before voter R's modification, what does our ballot look like? Well, we have B has been, or Trump has been boosted to the top of all the first R-1 voters, right? So maybe like there's another voter here. We don't care about these rankings. And this is just like some arbitrary ranking, right? We don't care about all these guys. But what we do know for sure is that Trump has been raised to the top for each of these guys. And then for R, before we change R, maybe R favors some random alternative K, we know that the last guy is B, just by construction, right? Recall that we had B is ranked last for all the ballots. So we also know that for all the ones after R, B is last, right? And then here, some other random alternatives. We don't care what goes on here, right? So this is what it looks like before R's modification. Now, after R's modification, we have the same thing. So on this side, we have everything is the same. And then we still have B here. But the crucial difference here is that we now have B swapped with K, right? So as we said, we're going to maintain ordering. So if K is first and we boost B, or Donald Trump, all the way to the top of R's ranking, like we discussed, we'd want to maintain that K is thus the second rank, right? Otherwise, we kind of mix up and jumble for no reason, and we don't want to do that. So we have the rest of R's rankings, and then everything else stays intact because we don't touch them yet. We're only talking about what happens for the R, for voter R, and recall that for everyone else, B is last by construction, right? So now we're given by the definition of R as a pivotal voter that B becomes the winner after the shift from profile A to profile B. I call profile A the one before the modification, profile B the one after, right? So by construction, in profile B, we have that B is the winner. See what I did there? All right, so hopefully that's not too hard to follow. So now we're going to make another observation, because what proofs are finished without a bunch of random observations. So we're going to claim that you'll recall this is the first thing that we wanted to show. Sorry for scrolling. We wanted to show that if the first R many voters rank B first, then B is going to win. So we're going to prove that, and then we're going to prove the one right after that, because they kind of go hand in hand. So this is an if. This is not an if and only if, it's an implies. So we're going to state that if Donald Trump is the winner, which we're given from profile B, then we want to show that the first R voters ranked Donald Trump first. So the proof, take profile B. we're going to claim that our strategy proof assumption guarantees that Donald Trump is always the winner. Okay? So how are we going to show this? Well, there's two cases. First, let's take all the voters on this end of the spectrum. So all these voters. So for any voter I indexed such that I is going from r+1 to the last voter, we are going to claim that B is still chosen regardless of voter I's rankings by construction. And why can we say this? So we're going to say that B is always chosen as the winner. So as winner, regardless of voter I's preference. And why do we know this? Well, refer back to the definition of voter R, right? So since R is a pivotal voter, this shift causes B to win. So let's see about all the other voters. Well, for any voter such that in, I guess, let's change color, we'll do in this camp, so including R. Any voter, for any of these voters, we know that B is still chosen regardless of also these voters' rankings because B is the top ranked candidate. So in this case, we can kind of go the AFSOC way. So we can say AFSOC B not chosen. What does this mean? Well, then this implies that voter, let me scroll out a bit. So voter I has an incentive to lie. Oh man, I can't spell. To lie. Why is this? Well, for all these voters, by construction, we have that they favor B first. So if B was not the winner, they would have an incentive to misrepresent their ballot, right? Because they have B as their first, as their top ranked candidate. So this actually violates the strategy proof assumption, because if they now have an incentive to lie about their choice, right? So in the case where B is not the winner, well, we can assume without loss of generality that like either A or C is the winner, or it could be any other voter. But the point is that, well, if A is the winner and suppose that like B has A all the way down here, voter 2 has A all the way down here, well, maybe there's some voter in this space where they can swap with A or with C such that, well, A no longer wins the election. Then voter 2 has an incentive to lie. So what we're essentially claiming here is that by the rules of our strategy proof assumption, it must have been the case that if B is the winner, then the first are many voters ranked B first. Okay, so maybe that was a little hazy, but I think that if you look at the profile, at the visual depiction of the profile, plus internalize really what it means to be strategy proof, then hopefully it becomes a little bit clearer. All right. So our next observation, kind of similarly, is going to show that if B is not the winner, then this means that voters R to N, let me try to keep the profile on the page. So voters R to N, I guess I'll erase this now. So these voters must have ranked B strictly last. Strictly last. So, oh, I remember why I did this now. This is, yes. So now we can just imagine that we're looking at this profile. That makes it a lot easier. So take profile A. By construction, we know B is not chosen, right? Because the R hasn't made the pivotal modification yet. So we're going to claim that B cannot be chosen, again, by the strategy proof guarantee. So for this one, I'm just going to go through the logic behind this. So we know that for any I that's in this camp, so the camp right before R, B is not chosen, regardless of this voter changing the ballot. We know that if a change did occur, so if B somehow randomly did win, then I would have had an incentive to lie, because we know that B is a top ranked candidate, right? So obviously these voters want B to win. So if somehow B did win, or sorry, we know that these voters do want B to win, and we're showing that B, and we're assuming that B is not the winner, right? So we know that if somehow voter I changed his ballot and B won, then they clearly want to make that change. Hence the fact that it would contradict the strategy proof guarantee. Similarly, for any I in the camp right after, so in the camp from R, so in essentially this group, we know that voter B is not chosen regardless of the of these voters changing their ballot, because in the same logic, if a change did happen, so if B did somehow win the election, well, B is the lowest ranked candidate. Nobody wants Donald Trump in this latter half, right? So if somehow they randomly made a change and then B B won, then voter I would have an incentive to change back, like to not make that change, because Donald Trump is the lowest ranked voter by construction. So they don't want B to win at all costs, all right? Like every other potential candidate is preferred over Donald Trump for some reason, right? So again, to maintain the strategy proof guarantee, it must be the case that B did not win given this profile. So a bunch of the logic is quite symmetric actually, but it takes a bit of contextualizing and really internalizing the profiles, just kind of getting which half you're looking at. And another thing that helps is that even though R technically doesn't have to be, maybe it might make sense to write this down. R doesn't have to equal n over 2, right? R doesn't have to be in the middle. It's just it's just nicer in terms of visualization to assume that R happens in the middle, and then you can kind of see, well, R is like the balancing factor maybe, but just keep that in the back of your head. R isn't necessarily the middle. It's just the pivotal voter. All right, now we proceed to step 2. We made it. There's only, I believe, 4 steps in this proof, so this is going to be a hefty one. So we're going to show that voter R, i.e. the pivotal individual, is a dictator. So we're going to show that no matter what the other people's ballots are, R always gets his top ranked candidate as the winner of the election. So in order to do this, we're going to consider kind of a special case of ballots first, and then we're going to go to the general case. So our special case is going to be that we're going to assume that our pivotal voter R prefers some candidate K. And we're also going to assume that Donald Trump is the bottom ranked candidate for everyone, for every single voter. So what does our profile look like? Pause the video and kind of try to map out this profile in the same way we did above. This shouldn't be too hard. All right, hopefully you did that. So we can clearly see that B is always on the lowest tier for everyone, right? So B is always on the bottom. And then we kind of don't know anything about everyone else's ballots, except we know that K is top ranked for R, right? Everyone else is kind of arbitrary. And yes, all good. So this is, we're going to call this profile C. And in order to modify this profile, we're going to say, let's raise alternative K. So the top ranked alternative for our pivotal voter to the top position for every voter, sequentially always, right? So we're going to modify our profile such that once K is at the top for all the voters, well, K is going to be the winner, right? No matter what. So this is, again, unanimity. I think I said it wrong before. Yeah, it's unanimity. So clearly, if K is top ranked by all the voters, it's going to be chosen because we assumed our social choice function was unanimous, right? So now we're going to say, let's start sequentially from voter 1 and then only go up to voter R-1. We're going to raise Donald Trump to the top. So this is kind of hinting at what we wanted to do in the original high-level overview. And so what is this going to look like? Well, Trump is still going to be on the bottom for voters R, this should be R to N, right? Because we're only raising it for the first 1 to R minus 1 voters. So this is actually going to look like this profile. So recall that we raised K to the top position, but then we're sequentially raising B, Donald Trump, to the top. So we're always going to maintain that B is strictly above K, and K is strictly below B by 1 spot, because of the fact that it was first for all the voters, and then for only the first 1 to R minus 1 voters, we're going to raise B above K, right? So K remains on top for all the other voters, and then for voters R through to the end, we know that B is still at the bottom. Trump is still ranked very low. All right, so now observe this profile, right? So as we noted, for the first 1 to R minus 1 voters, we have Donald Trump is at the top, and then for everybody else, Donald Trump's at the bottom, and K is still the top for the rest of the voters as well, from R to the end of the voters. So now observe one thing. We can see that one of the observations will come in very handy right now, because look, for voters R till the end, we have that Trump is ranked last, right? So this implies that Trump is not the winner by observation 3. If you scroll up, this is exactly what observation 3 says. And then we can also further say that by observation 1, this alternative K is actually the winner of the election. Essentially, this is the big boost hypothesis. We boosted B, Trump, and then we also boosted K, and we're guaranteed that Trump is not the winner, B is not the winner, so it must be the case that K is the winner, because big boost guarantees that either Trump or K is the winner, and observation 3 rules out Trump, right? Now what we're going to say is raise Trump to the second position for voter R. So now the ballot is going to look like this. It's the same one as before, except with one slight change. We're going to have Trump just sneak up on K, be right after K, right? So now we'd like to note this interesting fact. K is still the winner of the election. And I'd like you to pause the video and kind of think about why this is the case. All right, hopefully you have thought about it a little bit. So in order to answer this, we can go the AppSoc route. So if K is not the winner, well, then voter R wouldn't report this change. He wouldn't report this change, because he wants K, right? By construction, he wants K to win. But if we raise B to the second position, if we raise B all the way up here, and then somehow that results in K not being the winner anymore, well, why would voter R make this swap then? He wouldn't, right? But this is by construction, we made the swap, so it must be the case that K is still the winner. All right, so now we've shown that K must have still been the winner in this profile. So let's take a look again at profile C, and I've just copied it here again for convenience purposes. So this profile has B as last for everyone, and our pivotal voter R arbitrarily likes some random alternative K. So let's suppose that another alternative, we'll call it G, which is unequal to K. So G and K are different candidates, is the winner of the election. G has won. All right, so like before, we're going to raise B to the top, or Donald Trump, to the top position for the first 1 to R minus 1 voters inclusive, sequentially. So voter 1 is going to put B all the way up here, voter 2 is going to put B, and then it's going to keep going. We're going to stop at voter R minus 1. So the last B is right here at the top. Well, we still have the same observation. Voters R through the end to the end of the number of voters have B last. So what does this mean? Well, it means B is not the winner. So this is again observation 3. So we know that B is not chosen. And again, identical logic, we know that G is the winner by the big boost because we assume that G is the winner. So in this case, it's like not K or B, it's G or B. So we can use the big boost hypothesis to say that G is going to be the winner of the election. So we're going to raise B in voter R's profile again to the second rank. So we have profile F again. This is kind of, you should be recognizing this one. So again, K and B are in this position. K is still first for R and Trump is second. So first, we're going to suppose that B is not the winner of the election. Well, by the big boost, like before, we still have G as the winner. From observation 2, we can claim that once we make this swap right here, so once we have this swap, then B will be the winner, just by this observation that we proved, right? So voter R has an incentive to make the swap because they prefer B to G, right? We don't know where G is. G is somewhere down here is G. G could be like here, here, it doesn't matter, right? All we know for sure is that K and B come before G. So by the way preferences work, we know that voter R has an incentive to flip B and K because at least in that case, Trump wins, and Trump is in Kanye or R's mind better than this random, I guess I'll just keep G right here, is better than this random G, right? So this contradicts our strategy proof assumption. Hence, we know that B must have been the winner. So Trump must have been the winner of the election. So in this profile, in profile F, we have B wins, right? Trump wins. Well, what are we going to do? We are going to raise K to the second spot for the voters, for these voters, voters 1 to R minus 1. So this is going to be K here, all the way, K is going to be here. Maybe I should change colors just to make this a little bit more interesting. So then we're going to raise K to the first spot for the next voters. So we're going to have K up here, and then K up here. B is still the winner of our election, just by all the observations we have, right? So observation 2 still holds. B is the winner of the election because we've made this swap, right? So why is B still the winner? Well, for that, we can look to the fact that if B isn't the winner, then all of these voters right here wouldn't report the change that they made in bringing up K. Like every single one of these voters wouldn't have brought K up because they have B as the first person that Donald Trump is essentially the one that they want the most. So think of like all these, oh man, what happened? All of these like 1 to R minus 1 voters as like pretty much clones of Kanye, right? They all want Trump. So B is always first. So if somehow causing this rising K makes B not the winner, well, they won't report that change. So that contradicts strategy proofness. So this is bad, right? If B wasn't the winner, then the next voters, R plus 1 to N. Actually, this is incorrect. This should be R to N, right? No, actually, no, it is R plus 1 to N because we know R favors B. So voters R plus 1 to the size of the voter set, they would also lie because B is the last rank, right? So this is kind of the converse logic. So this again contradicts strategy proofness. So if doing something makes B not be the winner, then they would kind of lie and misrepresent because they already have B as their least preferred. So they would obviously want to lie to make sure that B doesn't win, right? So this contradicts strategy proofness as well. Well, this profile is kind of the same thing. What we have here, this profile right here, let's see if I can zoom out. This is equivalent to profile E. And we noted that K was the winner in this profile. So if we go back to profile E, this profile, this one right here. Well, we found that, remember all this proof that we did for if K was not the winner, then there'd be like some incentive to lie or misreport. So K must have been the winner. Well, our initial assumption for this same profile that turned into E, right? We assumed that G, some other alternative G1. This couldn't have been the case because we transformed this profile into E. So it's like congruent to E, right? So this means that B does not equal K, right? We know that B does not equal K. It doesn't mean that. We already have that assumption, or that fact, that B and K, that Trump and K are different people. So we know for sure that G couldn't have been the winner in our original profile C, the one which we made the modifications to. So this is kind of convoluted. We have a bunch of profiles going this way and that. We have profile C, profile F, profile E. But just remember that we took arbitrarily profile C, turned it into profile, maybe it's better if I do it this way. So we turned it into profile F, right? And then we found that profile F is the same as E. So maybe I'll just rewrite that. So F equals E, right? And in E, K1, right? So this implies in F also, K1. And we noted that K and Donald Trump are two different alternatives from our original, from like, we don't specifically for R, right? K and B are not the same. It's not possible. So if K and B are not the same, and we know that K won, but we somehow assumed that some other G was the winner that's different from K, well, this is a clear contradiction. So G couldn't have been the winner. Hence, even in the profile where everybody ranks Trump last, R is a dictator. So R, recall that R initially has K first, right? K number 1. So we proved that K is the winner, right? Hence, R always gets his first rank choice. So R is a dictator. He ranks K first, and K is always a winner, as we've shown. So in this special case, we've proven that our pivotal voter is a dictator. So if we scroll back, let's see. We've considered this arbitrary profile. We've done that. We've done the boosting. We've described the pivotal voter, and we've showed this is observation 2, this is observation 3, and we've just shown our special case. So nice, we have 2 steps left. We're going to now generalize this case. Instead of not just B is ranked last, B could be ranked anywhere, and we're going to generalize that our voter R is still a dictator, right? So let's march on. So we are now going to observe an arbitrary profile where voter R, our pivotal voter, ranks some K which is not B on top, right? First, we're going to drop voter B to the bottom for all the voters, right? So we're just going to put it to the end. From the above step, we know that K is the winner, right? When B is at the bottom for everybody, because that's what we just proved. We're now going to raise B back to the initial ranking one by one. And now we can also claim that as we continue to raise B back to the initial spot, either K or B is the winner. This is a simple application of Big Boost. So now we're going to consider this profile, profile G. We have B is first ranked for the first 1 to R voters, and there's some random voter who's ranked at the top. We'll call him A, but A is the same candidate ranked at the top for the rest of the voters. And then some random candidate C, call this like Donald Trump's son or something, I don't know, is ranked last for everybody, right? So we note that C is not the same as B and C is not the same as, well, our initial one had K, but it's just C. We want to note the uniqueness of this C, right? Okay, so let's carry on. We are going to raise C in each ballot. So raise means like boost to the top sequentially until we are at the pivotal voter for C. So recall, this is like the same thing we did for B, except we're just going to do it for voter C now, okay? So what does pivotal mean? It's same definition. It's essentially the voter for which once we make C the first ranked for that voter, C then wins the election. That voter is, we're going to denote him as M this time instead of R. So M is the pivotal voter for C, right? Well, notice M has his first ranked alternative as the winner. So this is like profile G. Whatever M we have is going to have its first ranked alternative, which is C winning the election. Observation 2 tells us that B is the winner because we have the first 1 to R voters putting B first. So B must be the winner from this specific profile. This is just a direct application of observation 2. So what we can observe here is that this pivotal voter M, which is for the alternative C, must have happened somewhere in between here. So M could have been like here or here, or he could have been like back here. It doesn't matter. M could not have been down here. So this is like not M, right? Because of the fact that once we get to R, we know B is going to win the election. So in order for C to have been the winner, the pivotal voter must have happened before R. The pivotal voter for C or M must have happened before the pivotal voter for B, which is R. Right? We can do symmetric logic to arrive at the fact that R is also going to be less than or equal to M if we just simply start with M as our pivotal voter for C, and then we're trying to like get R. So we kind of reverse the process. We can easily show that R is less than or equal to M. Well, what does this mean? This should bring back concepts vibes, hopefully. So we have A is less than or equal to B, and B is less than or equal to A. So this implies by the anti-symmetry of the less than or equal to relation, we have A equals B, right? So we have R equals M. So R is pivotal with respect to C, but recall that M is also the same thing as R, right? So R is also pivotal for B, for Trump. Like R is defined as a pivotal voter for Trump. But we also know since R equals M, excuse me, R is pivotal with respect to C. So R is like this kind of double pivotal voter, right? So we can claim that either B, K, or C, which is not equal to B or K, is the winner for our arbitrary profile, for this random profile, right? But C is not equal to B. So we must have that K is the winner because K is the first ranked choice of R, right? Like K, we initially claimed that there's some voter that voter R ranks some K unequal to B at the top, right? So we are essentially going to, oh, I see, there was some kind of mix up here. So right under here, we should have K. Yeah, sorry for the confusion. So essentially, yeah, we know that K is the top voter for voter R, and then we kind of like raise up B all the way. We raise B back to the initial rankings. So it could have been the case that B is at the top for R. This is kind of without loss of generality. This actually could be flipped, and we still arrive at the same results. But you just have to remember that K, the first ranked alternative for R, is K. So again, you already saw the white square, so you can tell we're pretty close, right? So once we have that C is not equal to B, oh, oops. So now that we have C is not equal to B, this implies K is the winner of the election, right? Because this is just, if you look back at the observations and the big boost hypothesis, we know that, well, it's one of these three are the winner of our elections. But we can't ever have that one of three candidates is the winner just by the fact that we're always raising things, we're always pairwise raising. So it's the big boost always says that whichever alternative we raise, either that alternative or the one that was the winner before the raise is going to be the winner. So this third guy shouldn't be here. So we know that C is not equal to B. Keep going to the eraser. So we know that C is not equal to B, right? Well, this means that we can essentially claim that alternative K is going to be the winner. And in order to kind of better explain this, well, we know from our arbitrary profile and the big boost that we have either B or K is the winner, right? And then from this new thing, we also have this and K or C is the winner. So what does this imply? This implies that K is the winner, right? This is just some basic concepts, some basic logic right here. Some propositional logic, I think is the term. So we show that even in this arbitrary profile, K is the winner of the election. Well, what did we say? We said R ranks K on top. And K must be the winner. We've proven that R is now a dictator. He always gets his top ranked choice as the winner. So let's also note that we assumed K and Donald Trump are different, right? We assumed, oh man, that was brutal. Assumed K is unequal to B, right? So let's just suppose that K equals B and still the top ranked candidate for R. we can show, and we'll leave this as an exercise to the reader, that R is pivotal for, instead of B and C, is now pivotal for this voter A. So like we have this random A right here. So we can show that R is pivotal for A and C, and then this implies that B is selected. So we still have that B is on top for R and B is selected, so R is still a dictator. So this is showing us that even in this general case, we've proven that R is a dictator. All right, this is kind of convoluted, kind of complicated, but hopefully it sort of kind of maybe went through that. We're essentially combining this fact of monotonicity. I'm going to finally say that word, but our big boost, which is also monotonicity, like formally, is showing us that we can like always guarantee either the alternative that we raise or the original winner is the winner after the raise. So combining this fact with observations that we've proved and just some sort of like pairwise swapping, we can show that even in the arbitrary case, this because of the strategy proof assumption, which you'll note we always use to prove the fact that once we get a winner, only that alternative can be the winner. Otherwise, we'd contradict strategy proofness. We can show that the winner is always going to be the top ranked candidate for R. And this is it. This is the infamous proof of the Gibbard-Satterthwaite Theorem. So we did it. You'll note that this proof was kind of short, I suppose, if you consider the amount of steps we did. We kind of created, I guess, like 7 or 8 different profiles, but that's just because we needed to consider a lot of cases. So kind of recapping, we finished that in the general case, we are still a dictator, and we noted that this B is not unique, right? We noted that K could equal B or K is unequal to B, and we still get R the dictator, right? We still get that R is dictator. So what we're saying here is that essentially it's pretty neat to show that the formalization of preference rankings, of aggregate choices, social choice functions can result in these like sort of very unintuitive notions. And I guess you can always tell your friends, hey, I can formally prove that dictatorships are the only fair voting schemes. So as promised before, we'll kind of go into some of the notes why this isn't as groundbreaking, as like earth-shattering, as paradigm shifting as it sounds. It is for theorists, but like they're few and far in between compared to politicians, right? So number one, interesting fact, this is independent of our choice of a social choice function. We never reasoned about F, right? We only reason about our profiles and the relative rankings, right? We never actually reason about the social choice function itself. We never care how F aggregates these profiles, these ballots, sorry, not the profiles, right? So this is pretty cool. It's SCF, social choice function agnostic. It doesn't mean anything in terms of the proof. It's just kind of a nice, happy coincidence, right? Strategy proofness is a really desirable quality, right? Like we would want all of our voting schemes to be non-manipulable, right? And well, if you go by that, Gibbard-Satterthwaite Theorem pretty much tells us that other than there's going to be one guy who always, there's going to be one Kanye, one enviable voter who always gets his first choice. And if that guy's Kanye, well, then he gets Trump, and I think that speaks for itself. But no politicization. Yeah, we're not getting into politics, right? So anyway, strategy proofness is really nice in theory, and we'd want our voting rules to satisfy this property, right? This is desired. But something that's interesting to note is that in order for whatever we showed, right, in order for this to happen, one, voter R, right, our dictator, needs to know all other ballots, right? Without this, we couldn't have come up at the fact that that the manipulation is something we couldn't have proven, we couldn't have reasoned about R essentially, right? Like R needed to know everything. We remember we had like voter 1, R-1, R, all the way to N. We knew all these things. Like these were known quantities, especially specifically known to R, right? But this is not the case in a real election, right? Like if I'm gonna go vote, I don't know every other person's voting preference. Let's assume we're not in the United States where there's only 2 alternatives. Recall Gibbard-Satterthwaite is defined where the candidates is at least 3, right? But it's also a nice exercise to think of why this doesn't hold for 2, why it's very easy to, why it's very hard to manipulate in 2, for when the choices are only 2. But regardless, it's very infeasible to say that there's going to be some voter, some manipulator, he's known as in the literature, that knows all the other ballots, right? So there's like strike 1 against Gibbard-Satterthwaite. 2, no other bad boys, right? We don't want other people to manipulate, because once other people lie, well, like there's no way you can tell whether what they're going to do, like the other voter could try to manipulate after R, in which case it's like a manipulation of a manipulation, and there's really no way to reason about that. So you're kind of assuming, we're making this assumption, right? And that's pretty crucial because, well, we can't just denote some guy as like, all right, you're going to be the manipulator, whatever you want is going to be the answer, is going to be the winner of the election, right? So another kind of unrealistic assumption we're making here. And then finally, we have, I think this is the key assumption that we're making, right? This is computational. What's the word coming after here? You guessed it, complexity, right? So we're assuming that this voter R, has the computational means to predict, right? So we're assuming, oh man, that was brutal, but whatever. R has this and power to predict whether a switch / misrepresentation of his or her ballot actually results in a more preferred outcome. Oh man, no, that was bad. Outcome. Right? So just because we assume that some R is our pivotal voter, is our dictator, how is this R gonna know, well, if he switches, like say there's A, B, C, D, E, right? And then somehow like E is the winner, right? So E wins. Well, how is he gonna know that maybe if I switch A and C, nothing changes. But if I switch A and D, well then D wins the election. How is he gonna know that? This is, I believe this is an NP hard issue. So overall, there's a lot of moving things, a lot of like unreasonable assumptions we make about Gibbard-Satterthwaite that allow us to prove this very, now it seems like very constricted, very restrained fact. And this is essentially what makes this theorem really nice to be able to prove formally, but also not too scary once we get the result, right? So overall, not really we kind of made it. Democracy isn't dead, right? If it was the case that it was really easy, if P does equal NP, then all right, this manipulator, whoever you are, like all power to you, as long as, you know, I agree with your candidate choice. But regardless, it's very important to note that another provable fact is that manipulation is NP hard or NP-C based on social choice function. So for some social choice functions, like if you look up STV, single transferable vote, the United States actually uses this in a couple of states, I believe, for like legislative elections. This is NP complete. So STV manipulation is NP complete. For other ones, it's NP hard, right? So obviously, if P equals NP, then we're kind of screwed. But it's as as it stands right now, it's very hard to be able to say that we can easily manipulate the outcome of a social choice function. So all in all, when the first time that Gibbard and Satterthwaite came out with this theorem, fun fact, actually, Gibbard came out with it, and then Satterthwaite also proved it independently. One of them proved it 2 years after the other. I'm not sure which one, but eventually it was found out they both got the idea, and so it was credited to both of them. So this theorem, again, claiming that the only social choice function that is unanimous in strategy proof is a dictatorship, it's kind of clickbait, which is pretty much what motivated me to choose this project, because it's really nice to be able to say, I can formally prove dictatorships are the only fair way to vote, right? That's going to turn a lot of heads. But once you break down the proof and really analyze where you're making the key assumptions regarding the strategy proof assumption, and also just the fact that computational complexity is very limiting in terms of what it allows you to feasibly do in practice, you'll understand that this theorem is kind of, as I said, clickbait. But like all theorists really like to say, it's really cool to internalize these things. I mean, Arrow's impossibility theorems says an even more general thing. Arrow's impossibility theorem. They state even a more general claim about than Gibbard-Satterthwaite, and it requires some other formal terms and properties that we want to be satisfied. But it's pretty nice to note that one, this idea of strategy proofness, non-manipulability, can be formalized. We can formally say what it means to not be able to manipulate a voting scheme. And then on top of that, we can use that definition to build this eventual theorem. So hopefully this proof wasn't too hard to follow. I think it makes sense if you really look at the different profiles we constructed and then keep the high level overview in the back of your head. And yeah, I hope you will use this fact to prank, but also kind of out big brain your friends and see their reactions when you say dictatorships are good. All right, thank you for watching.